Hello, everyone. Welcome to the UFS webinar series. I'm Bhavana Rakesh from National Weather Service, Office of Science and Technology, Modeling Division. Today, our webinar is going to be about the Earth System Modeling Framework in the UFS architecture. Our presenter is going to be Rocky Dunlap. And before we get started, I just wanted to give you a quick overview on how to subscribe to the webinar series and where you can find previous recording of the webinars posted by STI module. On the screen right now, I have the UFS community portal. It is at the URL ufscommunity.org. You'll find a lot of things here that's related to the new UFS. And when you scroll down, there is a Stay Connected section where you can subscribe to the webinar announcement. And when you click on that, it takes you to a Google form. Hang on, I need to sign in here. It takes you to a Google form where you can subscribe to the webinar announcements. And you can view previous webinars using this link in the Stay Connected section. It lists all the webinars that we have hosted so far, and past webinars have the YouTube recording of the webinar and also the slides that were used during the presentation. With that, I hand it over to Yan, who will be introducing the speaker to you.
Thank you, Bhavana. Hello, everybody. Welcome. My name is Yan. Yan Xue. I worked at the Office of Science Technology Integration. That's our branch is called the Modeling Program Division, headed by Dorothy Cook. So we are organizing this webinar to serve the whole UFS community. I'm very happy to introduce Dr. Rocky Dunlap, who got a PhD from Georgia Institute of Technology in 2012, majoring in computer science. Then he moved to University of Boulder during the period of 2014 and 2018, working on a variety of research. Then since 2018 has been working at NCAR as a project manager for the Earth System Modeling Framework, which is a software framework that helps build coupling different modeling components like atmospheric, ocean, land, and aerosol. This ESMF and the NUOPC he's going to talk about today are being used in all the major modeling systems in the US, including Unified Forecast System. So he's going to give an overview on the variety of functions in this software infrastructure. He has been playing very critical roles in the UFS modeling system architecture. He's a co-chair of a UFS system architecture infrastructure cross-cutting team in the newly formed UFS R2O project that cover participants from across different labs, university, and partners to build the next generation of operational system at NCAP. With that, I give back to Bhavana. Thank you.
Okay, thank you, Jan, for that introduction. Can you hear me okay and see my screen?
Yes.
Okay. Well, thanks for this opportunity to present on this UFS webinar. I wanted to just point out that the Earth System Modeling Framework is a multi-agency project, and we have a distributed team. So I just want to make sure I'm giving credit to all of the ESMF core team members. So they're all listed here as co-authors on this presentation. So for the talk today, I first just want to talk about the UFS, the different set of applications that are within the UFS. and the fact that it has a consistent system architecture across those applications. Then I'll talk about the role of the Earth System Modeling Framework and something called the NUOPC Layer within the UFS. And that covers a range of different parts of the architecture, including the driver, the model interfaces, intermodel communication, asynchronous I/O, and the use of data models, which is a way to do systematic testing of coupled models. I will mention a couple of cross-agency collaborations that are benefiting the UFS that have been enabled through the Earth System Modeling Framework, and then some information about downloading the code, getting user support, and training. So the UFS is a comprehensive coupled Earth system modeling application, and it supports multiple predictive applications. The operational systems that NOAA is providing are derived from the UFS. And at the same time, the UFS is designed as a system to be used, extended, and improved by the research community. I took this table that you see at the bottom from the UFS community.org website, and the purpose of this is to show the 7 different applications that are part of the UFS, and to show that each of these applications are made up of different sets of model components. So to support all of those 7 different applications, there is a unified system architecture. And this is important because to support that number of different applications, if we went down the road of trying to define a separate system architecture for each of those applications, it would be a lot of infrastructure to maintain. And so within the UFS, there is a concerted effort to make sure that all of the different applications are sharing the same architecture. And so this diagram is showing that it's a layered architecture with infrastructure pieces at the bottom, such as the model coupling piece, which I'm going to mention today, but other pieces of the infrastructure as well. There's the application layer with pre-processing, data assimilation, the forecast component, and post-processing and verification, and then a workflow layer that pulls all the pieces together. So zooming in on the forecast part of that unified architecture, we see that ESMF and NUOPC are a central part of that architecture. ESMF and NUOPC are the infrastructure within UFS that pulls together the independent model components and communication pieces and integrates them into a unified Earth system model. And this helps ensure a high degree of architectural consistency across all of the UFS applications, whether you're talking about the global medium range weather, the subseasonal to seasonal system, space weather, coastal application, are all sharing the same consistent architecture. This helps to eliminate duplication of effort across the applications, and it also helps with developers being able to more easily move between UFS applications because they see a similar code structure, a similar architecture between the applications. It helps with reusing code, and it also promotes a consistent architecture for each of the UFS applications as they are released publicly. So I've been using the acronyms ESMF and NUOPC. Just wanted to mention exactly what those are. Earth System Modeling Framework. It's a community developed, community governed software package. It has a way of defining standard model component interfaces and includes a toolbox of capabilities for building high performance coupled applications, such as grid remapping and parallel communication. So you can think of ESMF as a kind of general toolbox for building coupled models. On top of that, is a software layer that it's included with the ESMF distribution, and it's called the National Unified Operational Prediction Capability Layer. It is an interoperability layer that improves ESMF by standardizing coupling protocols. And so this really helps with interoperability across systems. And the NUOPC layer includes within it 4 generic extensible components that are part of the UFS. That's driver, connector, model, and mediator components. And we'll go into what the role of each of those components within the UFS. I also want to mention that other systems outside of the UFS are also leveraging ESMF and NUOPC, including Navy, global, and regional forecast systems at NASA, the GEOS data assimilation and modeling forecast system and Model E climate model, as well as the community Earth system model used at NCAR. And this has an advantage for UFS because the development of this infrastructure layer is, because it's being widely used, helps with creating robust software. So there's a lot of users and a lot of different capabilities are being added into the framework that then each of these modeling systems can benefit from it. It also helps with interoperability between the components. So for example, as the unified forecast system has needs to bring in model components from the community, we're able to leverage the NUOPC interfaces which are already present, and it simplifies the process of bringing those model components into UFS. So specific advantages of the ESMF and NUOPC layer within UFS. So I'll go through a few of these here. First of all, there's a unified driver. That means there's a single driver that's used for all of the UFS applications. This means that each of the applications does not have to come up with their own driver. The driver has an ability to read in a user-friendly text file that has the run sequence within it, and this basically specifies the order that the components that are included in a particular application are to execute, and when the communication between the components should happen. And this run sequence can be modified without recompiling the code. Model components under this unified driver can be optionally included or excluded during the initialization time, making it easy to turn these components on and off. And then this driver can also support multiple models of the same type, which has become important in the UFS. As an example, for the ocean component, there are 2 ocean models currently supported. That's MOM6, which is being used in the subseasonal to seasonal application, and the HICOM ocean model, which is being used for the hurricane system. And so this same driver is able to support those different kinds of components. This is an example of that short, simple run sequence syntax that I mentioned. You'll see that it has a looping structure. There is an indicator at the top that says at 1800. That's a time step indicator, meaning that's an 1800 second coupling interval. And then within that, there's a faster loop at 600 seconds. And this simple syntax here replaces what would otherwise be hundreds of lines of Fortran code. So you can see the order of execution of the ocean, atmosphere, and ice models. The MED stands for mediator, and that's that coupler component that's sitting in the middle. And then the arrow notation is the green arrows, which is indicating when the components are communicating with each other. This run sequence can also be, you can specify the kind of communication that the connectors are providing, the arrows. In this case, you see remap method equals redist, means there's a redistribution. So we're not interpolating between grids on those connectors, we're just moving data between different parallel decompositions. Another advantage of the UFS driver being a unified driver across these applications is the ability to have one place to connect to the data assimilation system. The unified driver provides access to the model states within each of the components. So you see in this diagram that there's some vertical connectors between each of the components moving up into the UFS driver, and that is indicating that data model state is flowing up into the driver and then can flow up from there into the data assimilation system. Through this method, all of the power of ESMF regridding is available to move the coupled modeled state to different grids if that's needed to match where the observations are located. And this approach here, I just want to mention one other thing about this approach here is it allows the coupled system to continue to operate in the same way, whether it's being run in forecast mode or whether it's being run with the data assimilation system. So we don't have to create another driver or figure out how to recreate that run sequence that I showed you before. That would be consistent whether or not the DA system is in the loop. So ESMF and NUOPC are providing unified model interfaces to all of the models that are part of the UFS. If you look at any of these components I've been showing in the diagrams, you'll see a NUOPC cap is sitting on top of each of those components. These are a small translation layer. It's usually only a single source file, a Fortran file, and it's a non-intrusive layer that sits on top of the model, and it provides essentially the interfaces into that model. The cap for each model provides to the driver, it tells what the required coupling fields and the coupling fields that it can provide to other model components. Those model interfaces support 1D, 2D, and 3D coupling fields and a wide variety of structured grids and unstructured meshes, including global and regional grids and the ability to map between global and regional grids. The caps are able to adapt to native memory layouts already used by the underlying model, so there is no need to allocate additional memory within a model component. You can reuse that memory as it's already been laid out. And then each of the caps code lives inside the model component's authoritative repository. And that means once a cap has been created for one application, it can be reused in other applications. So this really reduces the number of interfaces that we have to maintain in order to provide a variety of different coupled configurations. Optimized intermodel communication is provided by NUOPC, and that's through the component I mentioned that's called a connector. That's the green arrows in this diagram. The connectors are generated automatically by the driver, so there's no need for the user to write any code. And then at runtime, these connectors are responsible for negotiating the set of coupling fields that will be exchanged between the components based on a set of standard names. The connectors provide fast parallel communication. They can do different kinds of operations, and one of the huge advantages of these connectors is that at runtime, the connectors will negotiate the most optimized connection possible. So just because you're seeing this as an element of the architecture does not mean that it has to be an expensive operation. There is the ability with the connectors to actually share data between the components. If the memory layout, the parallel memory layouts match between components, the connector can figure that out and actually share pointers between components. So you get very good reuse of memory and very efficient communication. As you begin adding more and more components to a coupled application, the complexity quickly goes up. And so there's a question of how do you handle these multi-model coupling situations. The answer to that from NUOPC is through this special kind of component called a mediator, which is you see in the middle here. This is an example application. This is the UFS hurricane application with the UFS Atmosphere High Common Wave Watch 3, and this is being coupled through this mediator. Each of the components that participate tell the mediator what fields it requires and sends, and that mediator is responsible for basically managing the wiring and the flow of coupling fields, as well, including mapping, by mapping I mean regridding between the model grids, and even merging multiple fields coming from multiple models onto one common field and then sending that to another component. The mediator also helps to organize the code and provides really good separation of concerns within the code and keeps the code base organized. Just a little bit more detail about that aspect of regridding within ESMF. It is a high performance capability. So this is mapping in 2D or 3D space between different model grids. The entire operation is done in parallel. There's no point at which things have to be sent to one processor. We support a wide range of grids through this mechanism, 2D and 3D. There's a data structure specifically for observational data streams that are not gridded data, but just a stream of locations. And Cartesian and spherical coordinate systems are both supported. The regridding has, you can set what kind of interpolation you want to do as you're moving data between the grids. So there's a lot of out-of-the-box options, bilinear, higher order method, nearest neighbor, and then a first and second order conservative method are all available out of the box. And those connector components are all able to leverage all of those different interpolation options. There's options for setting masking and how to treat the poles, and it can be a bipole or tripolar grid is also supported. That's a typical grid within ocean modeling. And then access to this regridding can happen through a bunch of different interfaces. You can use the Fortran API. There's also a Python API to do this regridding from a Python script, and then there's a set of command line tools that work on NetCDF files, so you can regrid fields in one NetCDF file to another. One question that we have had is whether implicit style coupling is supported, because we're working with these individual components, and from an architectural perspective, it looks like that's only an explicit coupling mechanism. But with NUOPC, you can support an implicit coupling scheme where you have one solver that is solving over multiple components at the same time. So implicit coupling has some advantages over an explicit method, such as improving the stability of the model. It's more flexible in setting the time step, and there's advantages in how fluxes are conserved. So within ESMF, there's a structure called the exchange grid, which facilitates that. And there's this image on the left is showing you how the exchange grid is generated by overlapping multiple model grids. So this represents the surface boundary layer, and it's generated by overlapping an atmosphere grid over top of the different surface grids. And so when you have this kind of exchange grid in place inside a mediator, it allows you to do an implicit coupling type of scheme where you're sweeping between, let's say, the atmosphere model and the land model, and you want to do an implicit solve through that column. You can do that by using multiple phases and going through the mediator component. So there is a demonstration of this implicit coupling technique on GitHub, and I've provided the link there. And we've also done some work with GFDL, since they have done most of the work in pioneering this concept of the exchange grid, to compare the performance of the ESMF implementation of the exchange grid with the GFDL implementation used in their climate model. As far as asynchronous I/O goes, the ESMF and NUOPC infrastructure are at play here because we are treating the asynchronous I/O problem as essentially a coupling problem and leveraging the same capabilities that are used for the coupled model. In this case, the UFS atmosphere is divided into two subcomponents. So some of the tasks are responsible for the forecast, and some of the tasks are responsible for writing the model output. So we use the ESMF parallel communication when it's time to write out data to send data over to the write component, and that allows the forecast component to continue in parallel, so you get a more efficient use of resources. And there's the diagram on the right, the plot is showing some recent improvements between ESMF 8.0 versus 8.01, where we really tried to optimize this write component. And so the send times when the forecast is sending over data to be output has been improved greatly. There was an 85% reduction in the time spent in doing those sends. And so that work has been put into GFS V16 and will go operational with that implementation. ESMF and NUOPC are supporting as well incremental building and testing of the coupled model and different configurations of the coupled model. And that's by providing a way to substitute data components in place of a prognostic or fully active component. This enables hierarchical model development by allowing you to isolate coupling feedbacks within the system. So in the diagram on the left, you have what is a representation of the hurricane system, and this is working now, where you have a mediator, you have the ocean model, and then instead of the UFS atmosphere, there's a data component that is put in place. And this data component is just reading forcing data from file and providing that through the mediator to the ocean component. And because we're just reading in this data from file, it's a much less expensive component to run. We're not running the dynamic atmosphere, but it allows you to focus on the connection between HICOM and the CMEPS mediator, debug that, develop that, get all of that working, and then be able to bring in the fully active atmosphere component when the CMEPS HICOM connection is complete and validated. So this is capable. The reason this works is because the NUOPC cap does not have to. You don't have to change the interfaces in the mediator to connect this data component. You can put in the active component or the data component without any changes because the interfaces are the same. So now I want to talk about a couple of cross-agency collaborations that have been enabled by the use of this ESMF infrastructure. The first one is a collaboration on the what's called CMEPS. This is a community mediator for Earth prediction systems. Within the NOAA NCAR MOA, there's an agreement between NCAR and NOAA to work on various parts of the infrastructure and collaborate together. One of those elements is on intermodal coupling. And since ESMF and NUOPC are used within NCAR and NOAA, it has enabled this collaboration where there's a common mediator or coupler that's being developed in collaboration. The code is out there on GitHub, and it's had contributions from NCAR developers and NOAA developers. And it's being used, this mediator is being used in CESM, it's being used in the UFS S2S system, and it's also being integrated right now into the hurricane system, the new hurricane system called HAFS. And so this has been a really fruitful collaboration. The features of CMEPS are that it's ready to couple combinations of atmosphere, land, ocean, wave, sea ice, and land ice NUOPC components. So out of the box, it has built in those connections to those Earth system model components. It's a fully conservative 2D coupler, so it handles making sure that the land-sea mask is consistent during initialization, which is always a challenging part of putting together a coupled system when there's different grids involved. And it supports the time-evolving ice fraction. It's a data-driven field exchange specification. This means that when you've got the multiple components communicating with each other, you need to specify how fields from each of the models is mapped to fields in the other models, and can be a complex specification. But this has been boiled down into one file per application that specifies all the field routing, the remapping, and the merging of multiple fields together. There's automatic interpolation weight generation during initialization, automatic mapping from source to destination, and automatic merging of source fields to destination fields. It's all handled for you in this Mediator. It restarts the coupled system bit for bit. There's a Mediator history write option, and it's been designed in a very modular way so that because the Mediator is used in different applications, we need to be able to turn on and off various phases. And so it's been built such that certain phases don't have to be used in every application. And there is technical documentation out there on CMEPS, which is being improved every day, but there's already a lot out there. So I'd encourage you to take a look at that if you're interested in CMEPS. I wanted to show just a small code snippet here within CMEPS. This is demonstrating how concise the field specification is within CMEPS. So here we have about 10 or 11 lines of code, and this is the full specification for mapping fields from the ice component into the atmosphere component. So what was previously in the previous coupler, hundreds of lines of code and complex code, has been really simplified to these few simple calls that allow you to specify the kind of interpolation that you want to do, whether you need to normalize, for example, by multiplying by something like an ice fraction or ocean fraction, and then how to merge multiple fields together in cases where that's needed. So this is just an example of really nice, concise code within CMEPS. Another cross-agency collaboration also between NCAR and NOAA is called CDEPS. So similar acronym, but this time the D instead of Mediator is the data components. So the community data components are a set of open source NUOPC compliant components that are out on GitHub that provide those data streams that I mentioned that are useful for hierarchical model development, where you need to bring a data stream into the coupled system. It is easy to add new input streams. There's an XML-based specification of where you specify where your data files are located and the associated grids. And then there's out-of-the-box reanalysis and forcings included already with these data models, including core forcings and ERA 5 reanalysis are already available. The data models provide automatic regridding to move data between the input stream grids and the model mesh that you need. And there's multiple regridding options, all the ESMF regridding options I mentioned, including support for 3D regridding and including automatic support for time interpolation. So you can easily move data between multiple files that have different time slices per file into the time that's needed in the model. So it'll do all of that for you. There's a place in the code where you can add some custom calculations. So if the input data doesn't have every field you need exactly defined in the way you need it, you can customize that. It's fully compatible with the CMEPS Mediator. So these can be plugged into CMEPS and used for testing. And the data model share code can be called directly from prognostic components as well. And I'll explain what that means here in just a second. And then I provided the GitHub link there for anybody interested in looking further at CDEPS. So within CDEPS, the data flow looks like this, where you have multiple streams coming in, where each stream represents a set of files that have the same grid structure and the same temporal frequency. And so because you can support multiple streams here, you can be pulling in fields from different files that each have their own mesh or grid structure. They don't have to be the same, and they could have different temporal frequency. And then in the blue, you see that those different streams have been regridded to a common grid, and they've been temporally interpolated to the time requested by the model. So you're bringing in all these different streams onto the final grid structure that you need at the time that you need it. Now, if you set it up like a data model, then that means you can replace a component within the architecture with this component. So it becomes a stand-in for an active component, such as a data atmosphere or a data ocean. The other option is, because there's share code involved here, is you can just simply call that share code from within a prognostic component. So if, for example, you are, one place this is being used is within the HIMCO emissions component. If you need the ability to read in, from multiple files to do the I/O and to do the regridding, you don't have to set up a separate component. You can simply call into the share code and leverage this data model capability to ingest all that data, do the regridding, and do the time interpolation. So as far as getting involved, getting the code, if you are working with the UFS medium range application, which is the first public release of a UFS application, then ESMF will be installed automatically with the INCEP-libs externals, which has all of the dependent libraries included. If you want to work directly with ESMF, then we're on GitHub, and you can download and install the code there. We also have very active user support. So if you have questions, bug fixes, feature requests, any of that kind of technical support, the email is esmf_support@ucar.edu, and we'd love to hear from you. Any questions or concerns or anything we can help with. And then we also provide regular training opportunities on ESMF and the NUOPC layer, and I provided the link here where you can see upcoming tutorials and the previous materials there. So we hope you can join us for one of those tutorials. And that is the end of my presentation. Thank you. Happy to take questions.
This is Bhavana. If you have questions, you can type in the questions box. Okay, there are a couple of questions. I can read them out to you.
Okay, thanks, Bhavana.
Sure. What are the challenges if a user wants to implement the most updated sub-module model components in a public release UFS medium range weather app? The question is from Jai Sun.
The most updated sub-module model components. Well, I think that's a broader question than just the coupling part of this. I know that there has been a version 1.0 of release of the medium range application, and then a version 1.1 is being prepared to be released, and so there will be updated submodules. I guess I would say I'm not sure. I think you can attempt to update, parts of the components that you want to update, and build the release as the directions in the user documentation say, and then see, if you have any issues, and then if you do, then it would be appropriate to put those on the UFS forum. As far as official support, I think at the moment, and I'm not the release team lead, but my understanding at the moment is that the official supported releases are available, and then it would be, on you to figure out maybe how to do the updates until the next release. But so far, there's only been one release, so it is a challenge to figure out how to keep everything updated. sorry, it's maybe not the best answer, but that's what I can think of now.
Are there anybody on the call who want to answer their questions? We can unmute you. Bhavana, I could not unmute people. Do you want to?
Yeah, and people are asking questions in the question box. Maybe we can just read that out.
Okay. Yeah, continue with questions.
Yeah. The next one is from Deepthi Achutavarrier. She's asking, how does NUOPC CAP work with other tools within a model component like CCPP?
That's a good question. Right, so we are heading in that direction to have interoperability between NUOPC and CCPP. So CCPP is a common community physics package. The two, CCPP and NUOPC, were developed actually for different purposes. CCPP is mostly focused on the physics, column physics within the atmosphere. However, there are some emerging reasons why it would be nice to have greater interoperability between the two. An example of this is components like the land model, which are called from CCPP as a parameterization. Currently in the UFS atmosphere, the NOAA land surface model is used, and that's called through CCPP. However, there is interest in pulling the land model out by some people and having that be its own component. That would have an advantage, such as the land model could have its own grid. It could be a higher resolution surface representation than the atmosphere has, and could run concurrently. So there's some different advantages. So having some interoperability between CCPP and NUOPC is desirable. And I think there's been some just very preliminary prototyping of that, but it's not a fully supported capability at the moment.
Next one is from Rick Saylor. He asks, how does CCPP fit into the ESMF NUOPC framework?
Seems to be this, I think it's the same question.
Same question, okay. Next one is from Jimmy Dudia. He says, does each component handle its own I/O, or does it go through ESMF NUOPC?
Each component handles its own I/O. ESMF does have I/O APIs. So for example, you can write out the model state that ESMF knows about through a call to NUOPC. There's a NUOPC write API, for example, and that will output the state that ESMF knows about to NetCDF. But not all components that are using a NUOPC CAP are using that. It's an implementation choice that each component can make.
Next question is from Cliff Mass. He asks, can you talk more about the ability to move between dynamical cores in this infrastructure?
Another good question. I think that also seems to relate to me to the CCPP question and may further be, more impetus for CCPP NUOPC interoperability. And what I mean by that is, if you have a physics suite that is CCPP compliant, there's an advantage to being able to easily wrap that as a NUOPC component, and the physics, essentially the physics and the dynamics become separate components that you can control. They could run on different processor sets. You could potentially even have your physics running on a different grid as the dynamics. I know there's been some research on whether that's a good idea. And so that would allow more flexibility between the physics and dynamics, potentially at the cost of some additional communication, which may be worth it depending on what the application is. I think also CCPP itself for inline physics is really designed to facilitate changing out physics with different die cores. So from that perspective, the NUOPC layer wouldn't have to necessarily be involved if it's just purely inline physics.
Next question is from Han Meng Zhuang. He says, ESMF can do MPMD and SPMD, right? Is any one of current coupled components using MPMD?
Almost all applications that I know of are the single executable style. There has been work earlier on with the ESMF team to show that you can set up a multi-executable approach with ESMF. By and large, though, that is a minority of the usages to date.
The next one is more of a comment from Mike Egg to one of the previous questions. He says, yes, land can have higher resolution grid and hydrology, even higher resolution yet. The next question is from Evan Kalina. Yes, how does communication along connectors differ from communication that first passes through the driver? Why does communication among connectors bypass the drivers?
A good question. The driver's responsibility is to essentially call the model components in the connector. So it's the driver's orchestrating the sequencing. The connector, if you were to look at a diagram showing the overlap of the processors, you'll see that a connector between component A and component B is executing across all of the union of processors between component A and component B. So what you end up with is some of those processors are doing sends and some of those processors are doing receives. So the connector itself is really what is responsible for the communication, not the driver. The one difference there in the diagram I showed where the DA system was sitting on top and was controlling the forecast model, those vertical connectors allow data to be communicated from the model components up into the driver, and that way that model state can be passed further up into the system on top, into the DA system. So the driver can actually receive data from the components that are below it. But the connectors are what's actually doing the communication, and it's basically, it's wrapping MPI, the MPI layer.
So we have 12 more minutes. Anybody else have any more questions? I don't see any more questions.
Bhavana, we have a few more minutes. If anybody want to be unmute, we can unmute. They want to ask the question directly to the speakers. Anybody want to do that? Okay. Oh, okay. Oh, there's
hang on, there's somebody, Augustine Garcia has a question. He says, I tried to set up into the webinar announcement, but it asked me for permission. Let me look into that, Augustine. It could be because it's set up with the NOAA account. I'll figure out how to send the sign up information for you. So with that, I guess we can call this a wrap, since we don't have any more questions, and happy to give you 10 minutes back.
Okay.
All right, thank you, everyone.
Thank you, Raki, for the wonderful talk. Thank you,
Thanks.
everybody.
Yep, appreciate it.
Mm.